Sorry, little buddy. Stay right there. All right. This is kind of a really neat idea. Let's see. Let's say I want to figure out the length of this line segment, right? And you're going to say, well, that's not a line. I'm going to say, yes, it is. You'll learn later why that is. But I want to find out the curve length. We'll call it a curve. Just make you feel better. And a very interesting thing about everything we've learned so far, if I knew a volume element, like of the room, I knew a volume element, and I integrated over the whole area, over the whole volume, I would end up with the total volume, right? If I integrate over all the little pieces of volume, I'm going to end up with the whole volume. That's sort of like the chapter 6 stuff, where we broke things up into volumes. Like shells is a really good example. This little piece of volume, this little piece of volume, added up makes the whole volume. How are we doing? Okay, so if I want to know well, officially we call it arc length, we can call it. So if I want to know the arc length of this curve, I want to know how long this is. That's a difficult question, considering that it's all curvy, right? What's really strange is I can use integration to figure this out. If I can come up with an element of length, I can then integrate it to get the total length. So if I look at, for example, if I look right here, this would be a little dx, this would be a little dy, and then if I connect those, let me blow that up. So let me blow this up. Whoop. Dx, dy. This would be my dx. And thankfully, the really funny thing is, these are all lengths, right? These are all lengths. This is obviously a right triangle. So what's got to be true then?
Pythagorean theorem.
Yeah, Pythagorean theorem. So what would that look like?
Dx.
Yeah. Yeah, so ds squared equals dx squared plus dy squared. Meaning that ds equals the square root of dx plus dy. You're like, ooh. Great job, Jeff. Oh, squared. Okay. I'm getting one out of this. Now watch, this is kind of cool. This is the manipulation of stuff that you really need to be used to. I can write this like this. If I factor out a dx squared, and of course it comes out as dx because it's square root. So basically I'm dividing the inside by dx so I could put it on the outside. So what I'm really doing is this. I'm going to put a dx here, and inside I'm going to put an over dx squared. So I balanced everything. Because what's the square root of dx squared? Dx. So I multiply top and bottom by dx. Am I allowed to do that? Oh, hell yes. Because dx won't be 0. It's some finite value, right? So then what do I get here? I get 1 plus dy dx squared. So then the arc length would just be the integral. So if I was going from A to B, and this is f of x, the arc length would be the integral from A to B, square root of 1 plus f prime of x squared dx. So there's a larger idea. If I can write an element of blank that's true for everything across the entire whatever it is, I can integrate those and get the entire blank. So an element of volume, I can integrate the whole volume. An element of length, I can integrate the entire length. It's beautiful idea. Sometimes the D blank is difficult to set up, okay? Sometimes the integral is going to be crazy hard, okay, but the idea stays the same. It's really beautiful. So this is kind of surprisingly simple. I don't know if anybody got lost here, but that's just, why do you think I wanted to do that? Because my integral has to be integral D something to make sense. And it's really cool I can make it dx because I know exactly how far I want to measure. Going in, I want to know how long this is. Okay, well, you have to have a beginning and end if you want to know how long that is. So that gives me limits in terms of x. It's awesome. So maybe. So, I mean, if you want to look at that yourself, if you are eventually going to have to go to Calc 3, it's not a bad idea to kind of look at these, try a few out on your own, because it's going to build on this and back in Calc 3. You're going to say, remember this in Chapter 8. And you're like, oh, yeah, I do. A2 gets a lot freakier, so I'm just going to leave that. Normally, we completely review that in Calc 3 anyway. It's a little too much to try to get into at the end. Okay. So with all that said, I'm gonna just open it up to whatever you guys want to do. I think there's a few problems on the practice final that I ended up saying we do in class, like number 7. I think it was number 7. Yeah, in class. And I think the other set of problems from the book I said we do in class. So let's do those right now. What's number 7 say? What page is that from? 360? All right, let's see. Oh, yeah, cool. Let's see all that. Okay. So let's see, 360, 52. All right. I kind of added a little emphasis there. Because that word tells you two things. This is an optimization problem. So it's going to involve setting up the formula for the thing I'm trying to optimize, and then taking the derivative and checking out the critical numbers. So it tells you that it's an optimization problem, and it tells you the idea that you need to set a formula up for. Closest, of course, implies
shortest.
sounds like distance. Distance formula. Okay. So I want to set up. So closest is an extreme value of a distance, right? So it tells me that I want to set up the distance formula because then I want to minimize that. That's what closest tells you. It tells you those two things. It's the distance I'm talking about, and I want to minimize it. Do you guys see that? You see these kind of problems all the time. What point on this is closest to this, and so forth. And you do that in a lot of other higher level classes. This is your first little taste of it. I don't know if you guys remember, the distance formula, of course, involves this big-ass square root that's disgusting, but you don't have to, you can just minimize the square of the distance, in which case you will have minimized the distance. Thank the gods. So how do I do this shit?
Set the x, y equals to equation of y equals 8 divided by x.
Beautiful. All right, so I know that y is 8 over x. One point I'm dealing with is 3, 0, and the other point is a point on that graph, right? So tell me, what is a point on that graph? Give me a general point on that graph. And I love when people are like 4, 2. No.
X1, Y1.
X,
X2, Y2.
be less general. Because I know it's this
X2, Y.
graph.
Y.
No,
Either way.
be less general. Yes. I like some weird calculus Price is Right. Less, more, less detail. This is definitely on that graph. It has that information. X, Y could be anywhere. But X, comma, 8 over X is on this graph, obviously. I like it. So why do we, whenever you see this kind of problem, this is basically the way you do it. You identify a general point on one function and a general point on the other one. Now here I just have a point. Sweet. I could have another function, like when do these functions get the closest to each other? Which could be a comet coming in and the Earth's orbit. When do we get the closest? Well, the distance is 0 here, so we're screwed. You know, I kind of want to know how close is it going to get. So then I have one function, a point on that, and a point on that. I set up the distance between them, and then I minimize that. Because I can set the equation up. So what's the equation that tells me the distance between these two things? In fact, the distance squared. Maybe I should start with, what's the distance between 1, 4 and 3, 2? What's the distance between those two? Yes.
Plus 2.
Squared.
Yeah.
2 minus 4 squared. Sorry, I'm yelling. I'm getting excited. It's Pythagorean theorem, right? It's all in the xy plane, so distance between 2 points will be the x length squared and the y length squared. And then square root that gets this. So d squared between these two are just going to be x minus 3 squared plus 8 over x squared minus 0, right? So that is the function. So you set up a function that represents the idea they want you to optimize. In this case, make it closest. Right? That's a distance formula. And then you take derivatives to try to do that. Okay. So what's the derivative? Now here is not implicit, please dear God. This is the d squared function. So I'm going to say, okay, the derivative of this function is, I like it, cool. No reason to FOIL this out, is there? This will be 2x minus 6, is that cool? 2 comes down. Now this is 64 over x squared, right? So what's the derivative of that? Yeah, because this is 64 x to the negative 2, so negative 128 x to the, you're integrating. That's integration. We're differentiating. That really sucks. That's the old gear grinding I hear. I'm integrating, just trying to go back to differentiation. Take it in the shop. They're like, what'd you do this? Now, again, don't focus on that. That is the function. I'm trying to minimize this. I've taken its derivative. Now, how do I try to find the minimum? It's going to occur at a... The minimum would occur at a critical point. And you said it equal to 0 to find those. I like it. Now, obviously, x equals 0 would be a critical point here because it makes this undefined, but it actually makes the original problem undefined too. So it's not in the domain of my problem. Screw x equals 0. You guys see that? Critical numbers are where the function, the derivative is 0 or it's undefined. But here it makes the original problem undefined, so screw it. So I'm going to set this equal to 0. And then how do I solve that?
Take out a 2x to the negative 3. Right? No? Yeah. You sure? Okay.
This is 2x minus 6 if you don't have no x to the negative 3 though. Thanks for playing. So I would probably We get rid of that. Multiply by x cubed. Divide by 2. That don't look pretty. But this is where, like, synthetic division would come in handy.
Didn't you say you were dividing by 2?
Oh yeah, thank you. It makes it look a little bit better. Not much. We don't really have a way to factor that directly. But we could, again, so synthetic division is an awesome tool for being able to factor more than we normally can. What else can I tell you? Let's see. All right, so, I mean, did we talk about synthetic division earlier this semester?
No.
How many of you guys have seen synthetic division before? A few of you. All right, it's a way of doing long division of polynomials quickly. So, for example, if I wanted to divide this, and I didn't feel like doing long division, because I don't know if you guys remember how long division works up here. This is so bad. You guys should know this. 1, -1, 5. I put the coefficients down here. Bring the 1 down, multiply, add, multiply, add. This tells me there's a remainder of 5. If you did the long division, very quickly, just suffer through this for a second. Apparently you never have, and you have to. X goes in x squared x times. X times x is x squared. X times -1 is negative x. Change the signs. So it's the same steps as long division. Why should it be the same? Because x's are numbers. They have to work the same way as numbers do. Cancel, cancel, bring down the 5. X doesn't go into 5. So that's a 0. So you have like a 5 left over. 5 over x minus 1. So it's told me that that did not go in evenly. That does not go into that evenly. So what would go into this evenly possibly? It'd be something that has factors of 64 in it. So, I mean, you could try. So this is going to be 1, -3. I'm missing a squared. I'm missing an x. And then there's -64. So 4 works. So 4, 1, 4, 1, 4, 4, 16, 16, 64, 0. I like it. So you get x minus 4. Very quickly. See how every time I do this I have to change the signs? So synthetic says, let's just change the sign from the beginning. So 4 goes with x minus 4. Times all this shit.
Why did we choose 4 again?
So I was going to try 2, 4, things that go into 64. Because where would that number come from if this came from, let's see, how can I say this? If this came from something times something times something, where would that have come from? The product of these numbers here, whatever these numbers are right there. So what could possibly be in this little dude? Numbers that go into this. Yeah. If they're going to be nice. So x equals 4 is a critical number. We can check to see if it's what are we trying to find here? Minimum. All right, we can check out x equals 4. What point would that make? It would make 4, 2. Right? You can always graph this thing. X, y equals 8. Y equals 8 over x. Looks like 2 goes to 4. 4 goes to 2. 1 goes to 8. 8 goes to 1. So it looks like this. Whee! And then the point 30 is right there. So the possibility as 4, 2 looks like it would make sense. That looks like it might be the minimum. Do you guys get that idea? Does somebody have there's a slightly different way to do this specific problem. So here, this point has a tangent line that has a component going towards that, right? So what do you think is true about the tangent line at the point that is closest? What do you think is true about that versus the tangent?
Perpendicular.
Yeah. You can reason why that would be. Because it's coming closer, and it's got an element making it come closer. Right here, it's completely perpendicular. It's not getting closer or further away. And the minute it's over a little bit, it's getting further away. So that actually leads to another way to solve it, or a way to check it right now. Find the tangent line at that point and see if it's perpendicular to the line through there. That's quite a bit more work. That actually sounds like a good problem on its own. I like that problem. So we got a little sticky point right here. I understand that. This is why teachers that teach before this class need to know what the shit students need to know so they don't skip over shit like synthetic division, which is really stupid useful. There's no way in hell you're going to factor this thing if you don't know synthetic division. It just ain't. So I feel bad for you if you don't know it. I'm sorry. I apologize for my profession. I should have done better with you. Or if it's a chance you just missed that day, well then shit. So, what was the main idea here? That word was the most important word in this problem. It told you what function to try to set up, and it told you that it was an optimization problem. Closest. Minimize the what? The distance. That's what this is talking about. So set up a formula for the thing I'm trying to optimize, distance, and then take its derivatives to find the critical numbers. So that was 52. What was the next one on there? For number 7, 54. Now I would probably give you if I did give you a problem like this, I would make sure it didn't come out to something that relies on synthetic, since obviously a lot of you guys don't know it, which sucks. Maybe I'll bring my synthetic division thing tomorrow. I don't know. Just so you can have it just in case. 54, oh yeah. The largest circular cone that can be inscribed in a sphere. A radius R. Oh my God, it's horrible, but I'm just going to live with it. Who's showing? It's like I took a pottery class and this is what came in. So that's the setup. That's the visual of what they're asking. I have a cone inscribed in a sphere, meaning the parts of the cone touch the edges of the sphere. And they want me to find the volume, the largest volume of the cone. So a really good first place is, what's the formula for the volume of a cone? Yeah, 1/3. So a cone is cut out of a prism, which is a repeated shape. A cone itself, a pyramid is cut out of a prism. A cone is the simplest pyramid, believe it or not, officially in mathematics, and is cut out of a right circular cylinder. Cylinder is pi r squared h, so a cone is 1/3 of that, because you leave 2/3 of it. If you cut a cone out, you leave 2/3 of it in there still. So it's 1/3 pi r squared h. So notice how I only have one parameter to work with, and I have two of them in that problem, right? So I need to figure out the height of this cone based on the radius. All right, so everything I've just done for you is kind of like what you would have to do for yourself. Draw the picture, write the thing that they're asking me about, look at the picture, see how it helps you with what they're asking you about. So So the height, just to draw it in, is this, right? This much is the radius. Is that cool? That's nice. So I need to figure out somehow to see what that is.
Radius minus or height minus radius.
Let me be careful. Let me put this h. Yeah, this is all the whole h, right? Okay. So I need to figure out what that is. Now, it's not going to help to say that it's h, it's r minus h minus r. Do you see how that doesn't help? I mean, I need to figure out that in terms of r. Because I need to be able to replace h with something related to r. No, because it doesn't necessarily go all the way to the top.
Oh.
Let me do another extreme example of how I could do this cone. I could do this cone like this. There, that's inscribed in the sphere, right? In which case the height would equal the radius, wouldn't it? Okay. So, let me see. If I draw in another radius, let's just draw in another radius and see what that does for us. Poop, right? So let's call this something. Let's call this little element, this little piece y. So the h is y plus r. Now, when I drew in that other little r, and then let's do this. There's an r of the sphere, and there's also an r of the cone. Yeah, that's where I gotta be careful. This is the big ass r here. All right, because this should be r of the cone. I have little r already for the sphere. Is that cool? Gotta be careful about r's. Little r is the radius of the sphere. The cone has to have its own radius. Let's call that big ass r. Okay. All right. So is there a relationship between, well, what's the relationship I've got here so far with what I've drawn here? But, I mean, so here's our right triangle, right? So little r squared equals y squared plus big ass r squared. Yeah. That's a relationship from what I've drawn. Okay. And how did I pick where to put that radius? Right at the edge of the cone, of course, so it was related to that cone's radius. All right. I like it. So then y squared equals r squared minus big ass r squared. For example. Oh, let me think now. I need to figure out. So like y equals the square root of r squared minus big ass r squared. I mean, so the height now, so far, is square root of r squared minus big S r squared plus r. Is that cool? Just plugging this in. So far, so good. So far. But let me stop. The most important thing you have to get out of a problem like this is, why have I done what I've done so far? If I gave you this kind of problem, you'd have to be able to do everything I've done yourself. So what is it that motivated me to do all these things? I have an equation with too many unknowns in it, too many things happening. I need to equate them both to little r somehow, because that's the only parameter I'm given. So I'm trying to figure out from the setup what a relationship is between all these things. So I've got an expression for the height in terms of little r and big R. right? But big R itself can be changing. Like here, is big R the same as it is there? Nope. Okay, maybe. Let me see. Up. All right, so instead of me just standing here staring at this, because I obviously haven't even tried this problem before right now, I'm not going to do that to you, just stare at this. But do you see what the point of this is? Trying to get a relationship so I get something that has only one variable in it. R is the only true variable. Well, R is a constant. And I think they said, yeah, so my maximum volume has to be in terms of R only. So if they change the size of the sphere, I know exactly how the volume of the cone is that I can fit in there. Let's see. Yeah, all right, I can't think of it right now. There's another relationship I got to figure out for big ass R. But I'm not just going to stand here and stare at this all day. So, we're just going to move to the next one for right now. What is that next one? Besides 54? Oh, okay. This one's. So, have you guys looked at 59 yet? This one's after this. It's so beautiful. It's too easy. This is the kind of problem you get if you took 178 instead of 180. This is 178's favorite early problem. It is this kind of problem. And you maybe can see why. 178 is kind of like, part of it is it's business math, is what's the quick way to reference it. So a big part of business is figuring out where to set your price point so that you make the most money without scaring too many people away, right? So let's see, a hockey team, capacity of 15,000 people, that's the most you can fit. So if it turns out you need 16,000 people to make the most money, well then you just live with 15,000. I mean, with the ticket price set at 12 bucks, so if I got $12 tickets, that leads to an attendance of 11,000. Now what do you think the market analysis should show if you drop the price a bit? The attendance should probably go up, right? And vice versa. So somewhere there's a sweet spot where you can make money just right so that the amount of people that come give you the most overall profit. Does that make sense? So you don't necessarily want to pack a stadium, to be honest. That might mean you've dropped the price too much. For each dollar the ticket price is lowered, average attendance increases by 1,000. So if I drop this to $11, what does the attendance do?
12,000.
Yeah, so if I do 12 minus 1, this does 11,000 plus 1,000. If I do 12 minus 2, this does 11,000 plus 2 times 1,000. Do you guys see what I'm doing? This is something I try to do with my 110 students. Where does the variable go? Is the game to play? And hopefully you guys see the variable is the number of increments of dollar changes. I could also do 12 plus 1. If I took the ticket price up to 13, then the attendance should drop down by 1, right? Minus 1,000. So what is it in general then? If the ticket price goes down by X, then the attendance will go up by, no, there's a relationship, 1,000 times X, right? For every dollar I change it by, dollar, I'm changing attendance up. If I down 1 here, it's up 1,000 there. So down X here is up 1,000 X here. Now, of course, this is the number of tickets you sell. This is the price per ticket. So how to get the overall amount of money you made. number of tickets sold, price per ticket. Multiply them, and that's the function you're trying to optimize. That one's almost too easy, especially after just doing this one. So if I take this times this, that's the profit. That's how much money I'm taking in. At least from tickets. It doesn't go into anyway, in reality, you would have to take into the variable of how much maintenance. If you pack the stadium, it's probably going to cause more damage to the stadium, so then you have an increased maintenance cost. Thank God I don't work in finance. It would drive me insane. So then your revenue from tickets will be 12 minus X times 11,000 plus 1,000X. Multiply that out, take derivatives. That one's an easy one. It's kind of like related to if you plant one more tree into something, then the yield will change by this much, right? The yield will go down because then it's got to share the nutrients in that little plot of land. Are you guys with me? But of course, a tree, even if the average per tree goes down a little bit, maybe your overall yield goes up. Again, there's a sweet spot to reach. I mean, you guys want to finish this out? I mean, this is almost too easy. I don't know. Hopefully, is that good to say? This is beautiful, right? 12 times 11, 121,000. Plus 12,000 minus 11,000 is plus 1,000x minus 1,000x squared. Take a derivative. You get 1,000 minus 2,000x, and it turns out that if z is equal to 0, you get x equal to 1/2. Do you guys see that? So you actually want to change the price. You want to increase the price. Sorry, you want to drop. What did we say it was? Yeah, you want to drop the price by 50 cents. That'll increase your attendance by 500 on average. That'll be the sweet spot. All right, that problem is beautiful. Was there another one on number 7? I think there were just. Okay. And then there's that very last problem, I think it is. The other collection of problems out of the book. What page is that from? Oh, okay. So this is related to the rotating regions problems. Which one is the first one? All right, so they give you, this is a good review for these. Here's the region they're talking about. Good Lord. I'm going to start bringing my glasses with me. X equals 1 plus y squared. Y equals x minus 3, about the y-axis. Notice how the first thing to notice is that these are solved for two different variables. What's the easier variable to solve one of them for so that they're both agreed? Yeah, if I could solve this for x, they're both solved for x. And then hopefully that method that allows for it to be dx will work, right? It's not hard to solve this. It just involves plus or minus, and it depends on where the region is, and I might have to break it up and say, oh, God. So I'm kind of hoping that if I can make these guys agree on the variables, then the process I want to use will also agree with that. It'll be dy, since all my functions are functions of y. So what is this thing, what's the first thing I want to do here then? Yeah. So if I set these two equal to each other, I get a nice little y squared minus y minus 2. That's nice. So y equals 2 and negative 1. So I can kind of do a bit of a sketch here. Y plus 3, what's y, Jeff? So y equals 2 to negative 1, that's a negative 1. Yeah, 1, 2, 3, negative 2, negative 3. So when y is -1, x is 2 for this guy. When y is -1, x is 2. You do this in a different color. Let's see, where am I at? So I'm going from -1 to 2. So -1, this is 2. At 0, it's 3. At 1, it's 4, and it's just a nice 1, it's 4, and it's 2, it's 5. So there's the line segment. And then this guy is just going to be, so y squared normally is like this. Y squared plus 1 will be like this. So it looks like it does this kind of a thing, right? Is everybody cool with that? When y is 0, x is 1. That's going to be the vertex. It hasn't been shifted left or there's no other y piece. So it's basically going to do this kind of a thing. So that's the value of knowing what something is shaped as that requires less points for me to be able to graph it. Because I know the shape, I just fill it in. Yeah.
Isn't that saying, never mind, I got it. It's the y intercepts on that.
Say again, sorry?
You found the y intercepts instead of the x intercepts.
Yeah, exactly, because everything's in terms of y.
Yeah.
Yeah. All right. And I think you might have noticed that not the intercepts, but like where they meet.
Yeah.
Even I had to kind of stop and remind myself because we're so used to using x for everything. You got to kind of really keep yourself focused when you have functions of y. You really want to slow down on the graphs. I'm going to go around the y-axis. Now, if I did want to do integral dy, that allows me to use what method here? Washers, yeah. Don't freak out. Sorry, I just didn't hear you, that's all. All I heard was shh, and I was like, huh? Can you go good or bad? I don't know. So, well, as washers a good thing to use here. So here's my axis of rotation. So if I go out, what's my inner radius going to be?
1 plus y squared.
Yeah, so it stops at that wall. That's going to be the inner radius is going to be 1 plus y squared. What's the outer radius going to be?
1 plus 3.
Yeah. So the outer radius is y plus 3. Seems doable, right? I mean, more doable than one Jeff gave you in the test. No. Should have been too evil. So how do I set this up then? What's going to go here and here? Yeah, it's all about y. So from -1 to 2 for the y. What goes outside? Pi. And then,
Outer squared.
yeah, good. Y plus 3 squared minus 1 plus y squared squared. I like it. That one's set up pretty nicely. This is a huge thing pre-calculus was supposed to do for you, was to make it easy for you to make quick, rough sketches that were still decently accurate. The better you are able to do that, the quicker these kind of problems are. Because without this visual kind of anchor, it's really hard to set this up. So the better your anchor is, the better everything should be. Now this, I mean, sorry. I kind of sympathize with my teachers. They would go, and the rest of it is, do it. And I'm like, come on, the rest of it, you should know. But just to do this real quickly, so you get y squared plus 6y plus 9 minus 1 minus 2y squared minus y to the 4th. This is polynomial, right? I don't want to do this. Let's see. So you get pi, -1 to 2. Negative y squared. So let's see, negative y to the 4th minus y squared. Yeah. Plus 6y plus 8, I think it looks like. Is that cool? I mean, are you guys, does everybody agree that That's a difficult question to answer. Is the rest of that easy? No. I mean, what do you get when you integrate this? Yeah, negative y5 over 5 minus y3 over 3 plus 3y squared plus 8y evaluated from -1 to 2. And I just throw a 2 in there, throw a -1 in there, blah, blah, blah. Yeah, finish back. If you make a mistake somewhere in here, that's not like a truly heinous conceptual mistake. You should get most of your points. If you do this, set this up correctly, get the first thing started, and you make a mistake down here somewhere, a minus become a plus, or I almost don't care about that. I mean, the most important thing is to understand the idea. This is just throwing shit in there. Who cares? Oh, well, yeah. Still should get the right answer, but still, it's not nearly as important. You know how to do that. What's the next one? That was number 8?
Number 10 is the next one.
10? So see, they tell me the region is x squared plus 1, 9 minus x squared, about y equals -1. I don't know if you guys have noticed, but one of their favorite things, and mine too, is a down parabola, up parabola, median, right? Because they're the easiest to kind of set up to come out semi-nice with the numbers. So we've done a million of these, just about. What do you start? So it's the region bounded by these two things. You have to find out where they meet. So it's just the same way we did over here. You have to set them equal to each other. So you get 2x squared equals 8, x equals plus or minus 2, just to cut to the chase. Just kind of a nifty idea. Parabola coming down, parabola coming up, they meet. The overall shape they make doesn't have to be circular at all, obviously. So just to kind of draw this out. Here's 9. At -2 and 2, they're going to be 3. Looks like, well, no. -2 and 2 are going to be 5. There you go, Jeff. -2 and 2, they're 5. Is that true? That doesn't seem right. Maybe it is. Oh, I went the wrong way, didn't I? That's fantastic, Joe. Knock down there. So -2 and 2, they're 5. And at 0, they're 1 and 9. So this is basically what it looks like. The most important thing to keep track of is the top dude is 9 minus x squared. Makes sense. He's a down opening parabola at the top. Fantastic waste of space. And I'm rotating that around the line y equals -1. So I gave you 2 in a row. They're nice. They're both based on what method I'm going to use here.
Just for quadrants.
Yeah, exactly. Why wouldn't I use shells?
Isn't different than your axis?
Yeah, I want it to be integral dx, right? Because everything's in terms of x already. Cool. So in order for that to happen, since this is parallel to the x-axis, dx, that must be washers or disks, same thing. I like it. So then I can figure out my outer radius, my inner radius. Now here, my radius is going to be 1 further than normal because I'm going around a line 1 away from the x-axis. So again, I'm not really sure how else to say this. To figure out your radius, you just start from the axis and draw until you hit something. That's the inner one. So if it hugged it, the inner one would be 0. That's why it doesn't show up. Because we started the axis and like, I hit a wall already. All right, that's 0. That's why it doesn't show up. That's why washers and discs are the same. A disc is a special case of a washer where the inner radius is 0. So what is the inner radius going to be? How long is this? Well, it's this length plus 1. So the inner radius is x squared plus 1 plus 2. Yeah. And the outer radius is going to be, of course, yeah, it's going to be 10 minus x squared. 9 minus x squared plus the extra 1. And then it's the same process, right? So the biggest mistakes in that number, whatever it was, with the washer's disc on the test was a few people were using the wrong method at the wrong time. The really biggest common mistake was with the Shell's method, the R is not always just X or Y. It was around an off-axis rotation axis, right? So it had to be X minus 1, X plus 2, whatever it was. So that Shell's one, the very last problem on the test was a Shell's problem. And the radius can't be just X or Y because it wasn't on the axis. It was offset from it, so it should be longer or shorter, depending on where it was for you. So this will just be 10 minus x squared minus x squared plus 2 squared. And what would it go from to? Yeah, negative 2 to 2, that we already found out. Pop! Which is a whole other reason why I want it to be dx, because I've already got the limits figured out then. Now this one I'm not going to do You can do that. This is a safe one to use symmetry for, because it's already, the problem is symmetric around the axis I'm using, so it would work. And what do I mean by that? You can make it 0 to 2 and then double it. Now, if you're not sure when to do that, don't ever do that. That's fine, right? Just like your blinkers. If you forget them, don't ever use them. Okay. Did I give a Shell's one, hopefully? What's the next one?
16.
Oh, okay, good. I like this. 16 reminds you about, which is what integrals mean.